So I'm delighted to introduce Dr. Bill Graves from MIT. Many years ago, there was a thing called the Brinkman Report, which proposed building a whole series of synchrotrons in the United States by the Department of Energy. Dave Monkton was a powerful force in getting them all established, and he's the leader of the group that Bill works with. Monkton has since become more interested in neutrons, but the MIT group has always been a leader in this field of synchrotron design, and particularly novel design. As you can imagine, there's been a continuous effort over many years to make these things smaller, cheaper, and more accessible, with the vision of putting one in every physics department or research lab. So Bill's going to talk about the latest ideas along those lines. A similar machine perhaps might be built at Hamburg that the SEC is associated with, and there's some discussion which you'll hear about the possibility of building such a machine here in collaboration with the MIT group. That's the basis of the seminar. And finally, I was delighted to find that Bill and I have a common interest in sailing on San Francisco Bay and early English sports cars. Thank you, man.
Here. Those are fun.
Yes, awesome.
And shall I kill the lights? All right, thank you for having me. Thank you, John. Thank you, Patrick, very much. I appreciate it. Peter. I'm an accelerator physicist. I went to graduate school at UW-Madison and studying accelerators I'd already worked on where I started. And so there aren't many of us out there in the world, and we generally populate the national labs more than universities. And so I've tried to gear my talk today not so much to the specialists, but more to physics primarily, and an occasional chemist or biologist. But I'm going to talk about X-ray generation and about I'll give you some background. The exciting thing we're working on is the compact XFEL. So this is something that you could have in your lab. It can fit basically on the top of a laser table. But of course, X-rays started with small sources, and over the 20th century grew to these enormous things based on synchrotron rings and the big X-ray FEL at SLAC and when they're building in Germany and in Japan and so forth. They've evolved to enormous things, and these represent different generations of machines. We're going to try to bring that technology back down to a small size, and so combine some of those advances of the last century with the advantages of the small size. So I'll give you just a little bit of the background of what we do with X-rays and what impact those different generations have had before I dive into some of the details of our compact XFEL. And so this is actually the first paper that was published on X-rays, and Wilhelm Rontgen is the discoverer in 1895 and published this a couple of months later. And this is a picture of his wife's hand with their wedding ring, with the wedding ring he gave her on it, Anna Bertha. And this resulted in a Nobel Prize in 1901. And it shows you immediately one of what's still the major applications of X-rays, which is in imaging generally, particularly medical imaging, and its ability to penetrate materials. That's one of the things you get with X-rays, is the ability to penetrate. And it's been enormously useful. A few years later, actually quite a few years later, when was this, around 1912, this paper is written by Don Lally, who was the first to observe diffracted X-rays. And he realized he was having a conversation in a walk with a student, Ewald, who was trying to diffract visible light off of crystals. They blew out crystals from chemistry, and it wouldn't diffract. Of course, the wavelength is much too long. He was working with these mysterious X-rays, and they didn't know too much about them, but they thought the wavelength was short. And he suggested that maybe the crystal could be a diffraction grating for X-rays. And sure enough, they got the spots, and that's what those little dark things, they exposed the film and got dark spots at the diffraction rings. And so this is the first we saw diffraction. He won a Nobel Prize for that. And he tried to describe the crystal structure, but wasn't successful. And it was a couple of years later when the Braggs, I'll say son and father rather than father and son, because it's really Lawrence Bragg, the younger, who worked out the theory of a face-centered cubic structure for salt and was able to successfully predict the diffraction pattern. And this is still what we do today with our diffraction patterns. When you see all these beautiful protein structures and so forth, it's based on Bragg diffraction, and it really is not much different than the work that they did 100 years ago. And he was just 22. I don't know, how many students do we have today? Maybe half. So this is something to live up to. You don't have to get old and gray to do good work. He was just 22, a year out of his undergraduate degree when he worked out that theory. With his father, who was doing the experimental work, they together won the Nobel Prize in, I think, 1915. So that's very interesting. And so I'm not gonna go through all of the applications of X-rays, but these are two of the most important still: medical imaging in particular, and crystal diffraction. The tube that they work with is shown here. It's called a Crux tube, and it's shown schematically here. So this is actually a particle accelerator. We're going to talk a lot about particle accelerators today. This is just a low energy one, about 100 keV or so. I don't think they're old when they go up that high, but that's what they go through today. And all they do is accelerate electrons from a cathode. It hits an anode, and in that, when the electrons stop in the metal, they produce breaking radiation, Rontgen. That's what comes out, and that's still, your lab source today is still based on a very similar tube. It hasn't evolved very much. The primary evolution happened around 1960 when they realized they could spin the anode and thus not melt it. The limiting factor here is melting the anode with all the power that you put on it from the electrons. So they spin it, you get maybe a factor of 100 to 1,000 more X-ray photons than they got 100 years ago, but that's pretty much the end of the story with tubes. It's a very mature technology, and it can't really go for it. And so this was the first revolution in our ability to see atomic structure and to use X-rays. Was this first invention of the X-ray tube. I should mention the electron beam. They didn't know about electrons then either in 1895. Those hadn't been yet discovered as negatively charged particles. And they called them cathode rays, hence cathode ray tube that we use today. And it was around the same time that J.A. Thomson was able, using deflecting plates around one of these tubes to show that they were quantized charged, that it was a negatively charged particle, which is probably not the first time that the physicists got the sign wrong or something. We got the sign wrong on the direction of induction of electricity. Okay, so the second, so that's the first generation. The second generation is over the course of the 20th century, particle accelerators came to be. So these are accelerators like the tube, only much more powerful, and by going repeatedly through an accelerated cavity, you can get up to a high energy. It's actually not exactly how a modern storage ring works. They're at fixed energy, and there's an accelerator that injects into that. But the early ones, they got up by going repeatedly through the RF cavity where the high electric fields are, up to high energy. And so now, instead of being at about 0.1 MeV, they're at about 6,000 MeV. It's a very powerful machine. And synchrotron radiation was discovered, I think, in the 1940s, or it was first observed with the GE ring, right? At the 1948, General Electric visibly saw the radiation being generated by the electrons. At first, it was a nuisance for people making particle colliders, but they shortly realized that, hey, this is a very intense source of X-rays, and we can do much more interesting studies or get much more information about atomic structure with this very intense source. And so this second generation depended on making the beams relativistic. In that tube, what happens is the electrons hit the anode, and the radiation really comes out at about 4 pi. There's no particular directionality to it. But when you get those electrons up to relativistic speed, the electric field that they emit collapses into the forward direction. So it makes a very intense beam in the direction that the electrons are traveling. And so in a machine like this, the electrons go around in this direction, and the beam, there's actually a beam line in each one of these little triangular pieces. And so each one is looking at the beam, just looking upstream at the bending electron beam in there. And these are terrific. You can do great science with them, but they have some scale factors. This is a couple of kilometers around. You can see these cars parked in the parking lot of the APS outside of Chicago. and they cost about $1 billion each. So it's big and expensive and very powerful, about 1 trillion times brighter than that tube. So really you can do fundamentally different science when you have something that's 1 trillion times different than something else. An example we sometimes give is, if you have an abacus and you're going to do addition, you can move things at about once per second, or one floating point operation per second. Supercomputer is 1 trillion times more powerful. It's about a teraflop. And so that's the comparison between the lab source that we have today and the big sources of the synchrotrons. They're really qualitatively different in the science that you can do with them. I just want to say a couple of things about synchrotron radiation. It's a relativistic effect. So we take a relativistic electron beam, and it can go through a bending magnet where you just go through a dipole, and there's a kind of a spotlight effect as the particle goes. Or what's more powerful is to use an insertion device, usually called an undulator, which is, they look like a bunch of refrigerator magnets. They're a few centimeters in size, alternating polarity, and the electron beam just wiggles as it goes through that alternating field. And so that little series of bends all adds up in the forward direction so that all of the radiation comes out and adds to it itself. And I'll show you, there's a particular equation that called the undulator equation that shows a resonant effect. This makes monochromatic radiation very powerful, monochromatic tunable radiation. By varying the magnetic field, you can vary the wavelength that you go at. So it's a very flexible source. It's tunable, it's monochromatic, it's extremely intense. It's really the workhorse of modern X-ray science. And I don't know, there are probably 10,000 X-ray users at the synchrotrons. That's maybe too many. There's about, I know there were 2,000 at NSLS when I left some time ago at Brookhaven, and there's 3 or 4 of these big rigs. So there's many thousands of users doing their various science. And the great thing about X-rays, of course, is that it works over many spatial and temporal scales. At larger scales, and even up to medical imaging, which is centimeters in size, you do imaging. And then as you go below about a micron or so, diffraction becomes more effective. And you can see all the way down to the angstrom scale of the atomic structure itself. And this is because the wavelength is about 1 angstrom. Typically, we're working with 1 angstrom X-rays, or 12 keV is the photon energy associated with that. Sometimes I'll lapse into the keV nomenclature. And increasingly, we can look at different temporal scales. Traditionally, we've gotten structure, but now, recently, with the advent of very short pulse X-ray devices, we can look at how structure changes on a fast time scale. You can look at how a surface evolves, or how chemical reactions occur as these electron X-rays, the electron lasers come into existence. It really covers a lot of what we're interested in. So that was a description of the second revolution, and the second generation of X-ray sources, and it differed from the first in the sense that we got to a large scale, we used relativity to collapse that beam and make it powerful. We had a powerful electron beam that could give off a lot of X-rays. The third revolution is really just come about in the past couple of years, where we've learned how to make, instead of incoherent light, which is what you get from an undulator, there's a feedback mechanism where we can generate an instability, and the electrons will actually become bunched on the scale of X-rays, so that there'll be little packets of electrons, each separated by an angstrom. And so now, instead of radiating independently and out of phase, they become in phase, and the intensity of the light that they radiate then goes to the number of electrons squared rather than the number of electrons. Typically, I have 10 to the 8th or so electrons in one of these bunches. So if you go up by squared, you're going up by a factor of 10 to the 8th in intensity. So there's just an enormous increase in power. And that is typically what we see. We see a gain of about 10 to the 8th. And so this is showing roughly how the process works. We need a very high quality electron beam coming in. It's a higher quality beam than the rings can produce for technical reasons. The electrons relax into a set of states that's not very dense in the rings. But with a Linac, a straight accelerator, we can make a very bright electron beam. We introduce that into an accelerator, and it emits into an undulator. It emits spontaneous emission. That's another way of saying undulator emission or synchrotron emission. It's the same stuff we get out of the rings. But because of this feedback mechanism, the field acts on the electrons, they bunch. Because they bunch, they emit more light, and you get a feedback going until this process saturates, and you get up to this about 10 to the 8th times more power they emit in phase. And this has been a very powerful source. This is what Petra and John and others are using out in Slack now. So, so this is showing the LCLS, the Linac coherent light source at Stanford. And so this can make about a millijoule of photons in about 100 femtoseconds. That's just an enormous power. It's a 10 gigawatt peak power. Now, 10 gigawatts on a laser pulse is nothing for visible light, but as an X-ray pulse, it's really quite extraordinary. And it's transversely coherent. Therefore, a laser is not temporally coherent. It's not transform limited in the time dimension. And again, it's enormous. It's really quite a remarkable device, but it's about 2 kilometers of Linac and then another half a kilometer or so of undulator. There's the undulator and the light sources is a couple of meters long. Here it's 100 meters long, a little over 100 meters. So it's an enormously long thing, big national lab scale thing. This I'm claiming we can build on a tabletop. And I'll show you next how we intend to do that. So those are really the 3 generations. And here, this is a brilliance or brightness chart. So we use, I don't define my units here, but Brilliance has odd units if you're not used to them. It's the number of photons in the numerator, and then the 6-dimensional phase space in the denominator. You know, we have a transverse beam size and a divergence angle in 2 dimensions, in both transverse dimensions. And then there's also the spectrum and the time length of the pulse. And so brilliance is just how many photons contained in that 6-dimensional phase space, and many experiments depend on high brilliance. You need many photons, and you need them also to fit within a small phase space. So high brilliance is a goal. And you can see what X-ray tubes have done. These are the little tubes that we started with around 1900, and they got up a couple of orders of magnitude around 1960 with a rotating anode, but their performance has really plateaued, and they're the same now that they've been for about 50 years. And as synchrotrons came along, we walked up this curve, and the first synchrotrons were just accidentally X-ray sources. They were high-energy particle physics experiments that that people did X-ray experiments on. And then we started to design the rings really for synchrotron radiation. A second generation that used undulators, and a third generation that really optimized them. And now they're about to turn on the latest one at Brookhaven National Lab, NSLS-2. And we're fond of saying that's the last synchrotron that will ever, because they're really mature and they're, in many senses, not as interesting as the X-ray lasers. And you can see by this 10 orders of magnitude why that might be the case. So again, you know, we could fit an exponential curve to this, and the rate of increase of brilliance is twice that of Moore's law. The time to double in performance is just half of what the increase in chips. It's been tremendous, but it's not actually continuous. It's been due to these generations. First synchrotron radiation using relativity, and then getting coherent emission. And we've spent a long time trying to make more electrons to make more photons. That's not a very good idea. It's really better to be clever about how you make your photons, which is to act coherently rather than incoherently. And for people who actually understand the supply, I want to point out that this is the average beam brilliance, and so about 10 to the 20 for the major synchrotron sources. And this is peak. These X-ray lasers are so powerful that it doesn't make sense to run them at a very high repetition rate. The repetition rate of the rings is megahertz, and over here it's hertz, maybe 100 hertz. And you wouldn't want to go up to megahertz because all you would just have a tremendous welding torch instead of a useful scientific device. So these you really want to talk about peak brilliance. By peak I mean not the number of photons in a second, but the number of photons you get while the pulse is present within that 100th of a second. So just an instantaneous brilliance is maybe a better word. Okay, so we're going to try to take advantage, we're going to try to make one of these guys something small, but we're going to take advantage of relativity and coherent emission to make all this stuff small. And I guess I just mentioned, for folks in the room here are familiar with this publication in Nature a couple of years ago. There's a famous one doing femtosecond protein nanocrystallography. And the idea here is, with these short pulses of X-rays, they can put this enormous flux onto a crystal, and you get your diffraction pattern. At the same time, the X-rays are so intense that you're causing tremendous radiation damage, but if the pulse comes in a short enough time, you get to diffract your photons before you destroy the sample. And what these different plots show is that it's a lot of plots, so it doesn't look like much, but there's a factor of 10 or 100 better signal to noise for a short pulse than for a long pulse. And short, in this case, is 10 femtoseconds versus 200 femtoseconds. And so, in crystallography, you have to make a crystal, and the crystal is a tremendous multiplier of your signal. You get coherent addition of the scattered X-rays when you satisfy the Bragg condition, and that enables this very weak scattering that's going on to be effectively amplified so that you can measure. And the hope is that with FELs, we can get away from crystallography and go toward possibly single molecule imaging or diffraction. And the great advantage of that, there are many materials, of course, that you can't crystallize. You can't grow crystals either in a large enough or have an ability to crystallize them at all. So that's the goal. And this stuff is tremendous, but I do want to point out that there are 80 co-authors on this paper, and there's about 20 institutions represented. And in that sense, it's looking less like an X-ray experiment and more like a high-energy physics experiment. And that's not necessarily how everybody wants to run their experiments. You know, we like to be in our labs and go in there and get our data and get out, you know, not plan it for a year in advance and coordinate with 100 other people. So these big machines do great science. And what's the role for a compact source? You know, a lot of times we see, well, here you can just go to the major sources that, you know, what does this compact source that you're talking about have to offer that we can't get otherwise? So I'm just going to scroll quickly through some reasons that you might want to build it. One is, and this is especially relevant now with the Ebola scare, is that you can't bring, you know, these bio-level 4 pathogens into any of the synchrotron sources. You can't travel with these proteins and use them there. And so for a compact source, you can, of course, have it in your laboratory with the appropriate safety mechanisms. For the pharmaceuticals, there's a dozen pharmaceuticals just around the MIT campus that would love to have this device in their lab. Right now, they have tremendous screening programs, and the travel time and the turnaround for them is really important. And if a ring is down for a month for maintenance, it's a major deal. It means that their ability to characterize those structures is gone for that amount of time. There are, even at the national labs, there's the National High Field Magnetic Laboratory, a spallation neutron source, where they have, you know, intense sources, but not an X-ray source. And to have this mixed in, these multi-modality devices would be enormously useful. A few years ago, we got invited to the Louvre, which was a lot of fun. There's actually 200 scientists in the basement of the Louvre studying these cultural artifacts. And they'll, on the days that the museum is closed, they'll bring the painting downstairs and put it. They've got a particle accelerator down there now. It's about 30 years old. They want to replace that with a new one. And so they're very interested in this. And so the common theme here is to bring the accelerator and the X-rays to the science rather than the other way around, because there are lots of situations that doesn't support that. And so we want to, as I say, we want to bring, you know, coherence, synchrotron radiation, and the compact size into something that fits in a room. And this is a picture of our actual design for such a device. So the resolution is not too good there. I'm going to wait. I'll describe the components when I get to the big picture. And you might ask how we do that. How do we take, this is the accelerator right here, this thing that's 1 meter long, 1.3 meters. How do we get hard X-rays out of such a small accelerator when it takes such a big one? And the key is this equation, in fact. This says that the wavelength of the X-rays is equal to the wavelength of the wiggle period, which could be a laser period, or it could be the centimeter period of the static magnetic undulator in the synchrotron, divided by 4 times gamma squared. Gamma is just the electron beam energy in units of rest mass. So if you want to make X-rays in a synchrotron, you can only make magnets with centimeter periods because you need a strong magnetic field. And so if you just put that into this equation, you can ignore these other terms. Then you need a gamma corresponding to an electron beam energy of a few GeV, 5 or 6 GeV, and that's why those accelerators are so big. We can do just the same thing with a laser field. A laser field is a propagating electromagnetic wave. It's not a static magnetic field. The electron actually doesn't know that. If you were riding on the electron toward that static magnetic field, if you were to put yourself into the rest frame of the electron, it would look like, that magnetic field would look like a propagating electromagnetic wave coming at you. It really is indistinguishable in its rest frame, but it's got a much longer period, of course. So this is centimeter period, the laser field is micron period, that's a factor of 10 to the 4, 10,000. And since if we take this down by 10,000, means our gamma can drop by 100, and my accelerator can be 100 times smaller than the big one. There's no real magic here other than trying to have a powerful laser field to go in. And this is saying pretty much the same thing. Some people might be more accustomed to the scattering picture of inverse Compton scattering. I just gave the undulator picture. It is really like an undulator. It's like synchrotron radiation. There's no difference. The scattering picture, you have a laser photon coming in, hitting the relativistic electron, and then gaining energy and being backscattered at a much higher energy. But the equation is just the same. It's the same process. And I'll say the intensity of the X-rays, because these electrons have no particular periodicity to them, they're randomly distributed, there's a phase cancellation. Not all the fields add up in phase, so that the intensity only goes as linearly with the number of electrons. And so that's not a coherent process. Okay, so the basic, I'm going to go through now what this compact facility looks like a little bit, talk about some of the technical components. There's an RF gun which produces bright electron beam, and typically this goes up to a few MeV in energy. So the electrons are photo-emitted from the cathode. We strike the cathode here with a laser. They're photo-emitted and very rapidly accelerated in a strong field, about 100 megavolts per meter, up to a few MeV. And then they're focused by a solenoid and coupled into a Linac. And this is exactly how LCLS works, except this 1 meter is 2 kilometers, and we're just a meter. We have a strong outer shield in here too. And then we collide with a laser, and we actually store the laser in a cavity, so it rattles back and forth here, and multiple punches can then collide with that laser. This Thomson cross-section is very small, so when we scatter laser photons, it doesn't even know anything's happened, and we can reuse those lasers. We only get something like 10 to the 6 photons out of this, I don't know, 10 to the 15 or so photons in that laser packet, so it really isn't moderated at all. And then, so we get lasers, we get X-rays come out in the same direction that the electrons were going. It doesn't matter if it crosses at an angle, they're going to go in the direction of the electrons. And so we have an X-ray optic and detector, and we dump the electron after going to the dipole. This whole thing, as I showed you in the picture, fits in a pretty small space. So this is what it actually looks like. This is actually containing components that we've designed and are ready to build. And it includes substantially all of it. Sometimes you see these new accelerator concepts. They talk about a laser plasma wave field accelerator that it's only a centimeter long or something, but they don't show you that there's a building actually full of lasers to drive the darn thing. But this is all of our power supplies fit into a couple of cabinets. It takes quite a substantial laser. It actually amuses me that the laser in this setup is larger than the accelerator. And that's because we have quite powerful amplifiers to produce. The stronger we can make this laser field, the more X-rays we can get out. So we work pretty hard to make a strong laser field. There's another laser that drives the photocathode. The photocathode is here. You see next to the human figure, there's the sharp Linac, some bending magnets. This is called a chicane, where we electrons, and then they collide in this area. And it's unlike the big facilities, our X-ray beam is quite divergent, and so the one effect that has is to make the X-ray beam lines very short, typically a half a meter to a meter long. So the whole thing is very compact.
Can I ask you a question?
Sure.
Since you don't have a storage ring, what luminosity should you have for the electron beam to make it efficient?
Well, we don't, for Linacs, we don't really talk in terms of luminosity.
Well, you have to have a bunch so that you will have some distilling and actually getting the pumped up electron beam. So.
Well, I can tell you what the emittance is, which is a measure of the transverse phase or the amount of charge, it's about 100 picocoulombs.
So can you achieve with this electron source the required, enhanced electron beam that can be used to actually study this, or it will be very,
Well, if we have to beat a rotating anode by a lot, right? What does a rotating anode cost? A couple of $100K for a really good one. So this is a few $1 million, and so it's got to beat it by at least an order of magnitude. But in fact, we're up by a factor of about 10,000. So our flux is typically 10 to the 10th to 10 to the 11th per second. An undulator beam line might have 10 to the 14, but in a bending magnet beam line is also around 10 to the 10th or 10 to the 11th.
So you're going to have the beam with bunches, right? It's still continuously.
Right, they come at a well, it's got a pattern to it, but it's at about a kilohertz, right? That's right. They're short bunches, picosecond long bunches. So I talked just a little bit about the technology. This is the project itself. I don't know, probably most of you haven't been out to SLAC, but if you go and you look at the equipment sheds, there are very large power supplies driving everything. To drive this whole thing, there's a klystron, and it's this big, and it drives out Linac and produces the 20 MeV electrons. It drives the gun too, and something else called the Diffraction cavity. Sammy Tantali out at SLAC has designed this Linac. It hasn't been built yet. There's currently one under construction. He's building for a prototype. And it's quite different than existing Linacs. It is still RF, and it's still a chunk of copper like they are, but it's very inexpensive to manufacture. Typical manufacture is, this is actually, it's not a cutaway view, it's actually built in half, so they can machine half the Linac like this. It's actually a quarter, and then they stack them up. And these little things are the RF cells that contain the strong fields. And normally, the power, the RF power, is coupled down the hole that goes right down the middle where the electrons go. But this has a very different type of coupling. Each one of these is separately coupled to waveguide. This is the waveguide here, and there are small holes that couple into each cavity separately, so that each cavity can be extremely efficient. The Q is very high on this, or the shunt impedance we would describe it as is very high. So it uses very low power for the amount of energy it gives. It's also very inexpensive to manufacture because instead of stacking up all these separate discs and washers, they would have to separately braze all these different things, machine out. If you got 100 cells, they would have to machine about 4 parts per cell and then stack them up in a big braze. Here they can just put it on the machine and numerically CNC the whole thing out, and then braze the halves together, and it's quite inexpensive to build. The lasers I won't go into too much. I'm not a laser guy. For people who are interested, this is what's happening. I want to say they're quite powerful. We get 100 millijoules at a kilohertz coming out of this one, a couple of picoseconds long. And these are these cryogenically cooled ytterbium-YAG amplifiers, which are very powerful. They have been demonstrated up to multiple kilowatts of average power. We're running at, I think it's something like 100 watts. This shows the interaction area without the vacuum vessel on it. So all the accelerator stuff is up here. The electron beam comes through these quadrupole magnets, which act just like lenses do for optical light. And we need, in order to have an efficient interaction, it can be considered a scattering process, and so you want to make the targets dense. We want the laser to be small, so there are lots of photons in small volume, and we want the electrons small too. And the X-rays are coming out at a large angle. And so those are just named 3 different beams, X-rays, laser, and electrons. And they each need lenses with a large numeric aperture nearby in order to hit the small focus. So the geometry is tough on this, but doable. And so we have these quadrupole magnets, or the lens to the electron beam. We focus that down to about a 3 micron size at the interaction point. The lasers focus down to, I think, about 7 microns width there, and then oscillates in this cavity. The electrons are bent, and then we have something called a Montel X-ray optic, which is very similar to a Kirkpatrick bias for you X-ray scatterers out there. Device, and it's gotten close because we're diverging quickly, and so we have to capture that beam quickly. And then the detector is typically about a meter away. This is actually showing the sample. I think this is something like 5 centimeters upstream of the detector. It's very close by. And we just dump the electrons. We throw the electrons away from that. So we've done a lot of simulations. These are the same programs used to design LCLS, space charge, and all the different effects that we know about in accelerators. This is showing the electron beam at the interaction point. This is the transverse dimensions showing in microns that we've successfully focused the entire beam down to under 5 micron by 5 micron spot. And so that's going to be our X-ray, that's our X-ray source size. It's actually a convolution of that in a laser, so that the X-ray source is a little bit smaller.
This one is data or simulation?
This is all simulation. This is, I'm not going to show any data in this talk. It's simulation. But it's the same simulations that we have used to design all the recent high brightness electron devices. This is showing the time dimension of it. So it's about a picosecond long or so. These I don't think you care about too much. This is okay, and then we can take that electron beam. We do this is a full 3-dimensional time-dependent simulation. Same with the laser beam, including the nonlinearities of the cavity and the D integral and so forth, and combine that into a Compton program to calculate the X-ray emission. And this is showing what we get out and its opening angle. It's a fairly wideband process. This is where I've windowed it at a 5% bandwidth. This is the radiation that comes out within a 5% bandwidth. You can see it's out to about plus minus 10 milliradians, which is about the maximum we can collect with X-ray outputs. If we limit that to a smaller bandwidth, or we have optics that only collect a smaller bandwidth, you can see that that's emitted into more on-axis. There is a Doppler effect, actually, a Doppler shift. As you observe the X-rays farther and farther off axis, the effective velocity of the electrons relative to you is different, and there's a red shift in the emitted spectrum. It's also true in an undulator, but it's less pronounced because of the higher energy. And so we have red-shifted photons come out off axis, which is why when we limit ourselves to a narrow bandwidth, we're primarily on axis.
Why is there noise in a simulation?
There's 10,000 particles, and I use a density plot, so that's just a pixelated density plot. Sometimes I plot the particles, but you can't see how the density varies. So this is giving Flux and Brilliance, that's about Flux and Brilliance in this device, as a ratio of half angle. So as you have a very high brilliance on axis, but not as much flux. So as you collect more flux by having a larger opening angle, out to about 5 milliradians or so, you're getting virtually all your photons. And depending on your bandwidth, you'll have more or fewer photons. So for our primary design parameters, we're getting about 5 to the 11 photons out in this device. And I just compare that now with the bent magnet radiation. They typically put 10 to the 11. Actually, just went to look at all the crystal active lines into 100 micron by 100 micron spot, 50 by 70, 300 by 200. It's always around that. So we're putting a similar number of photons Our source size is very small. You use 1-to-1 imaging, and you get it into a small spot. We've done some simulations of the optics too. This is not a 1-to-1. This is a magnification of 3 for a particular application. And so we're making kind of a 20 micron by 20 micron spot here and showing angles. So this is at the focus of the X-ray optics and telling you what kind of throughput we get from these optics. And so that's a summary of the parameters. I don't think we particularly need to go through all that. Are we doing that time? Okay, okay. Because what I want to get into is now the coherent. I haven't yet presented the coherent. This is what we could build tomorrow. We've done a lot of work on it, and it's a low-risk design. But we want to go to a more interesting machine by adding some.
You just say none of what we're going to. You actually build something, not just design, but a physical machine.
Not a physical X-ray source, no. There's parts of that equipment in-house, but there's not an X-ray producing device. There are many people who've done inverse complement scattering experiments to prove that it works, but nobody's built an optimized X-ray source yet. I just want to show this one quick study on looking at charge. This is a quick set of simulations where I typically work with about 100 picocoulombs of charge and getting flux of about 10 to the 7th per shot out within the central bandwidth and particular brilliances. We go down in charge, we go down in flux, but not as rapidly as you would expect, because the electron beam becomes better quality. LCLS has seen this too. Early on in FELs, we're all designing for a nanocoulomb of charge, and what we've all discovered is that these things work a lot better at lower charge, basically because we avoid a lot of collective effects that damage the performance. And so this is pretty interesting. At a picocoulomb, we get down to 10 femtoseconds. This is doing nothing tricky, and we get about 10 to the 5th photons per shot out. Peak brilliance is actually going up over the high charge case. It's gone up from 10 to the 20 to 10 to the 22. That's because of the improved electron beam quality. And the average is staying about constant. So really going down in flux, but brilliance going up as you go down in charge.
Is charge kind of like the electron beam current, or what? Is that to be thought of as the number of electrons coming down the pipe per pi unit, or what?
Is what like?
Charge. Well, what is charge?
We usually talk about charge in a single bunch, and then we have so many bunches per second. That's what we do. So typical design parameters are we have 100 picocoulombs in 1 picosecond. That's 100 amp peak current.
When you bring it down, are you decreasing the bunches per time, or the number of electrons per bunch?
Number of electrons per bunch. It's the collective effects that kill us. And by going down in the number of electrons per bunch, we get rid of the collective effects. Okay, so far we've been talking about this case, where there's no phase relationship between the emission of the different electrons and you get noise out. And what we'd like to get to is where we bunch the electrons. We arrange them in the angstrom scale. This is just what an FEL does. And then we can scale up by this factor of 10 to the 6 or more in intensity. That's the goal. And can we do that as low energy? And we mentioned when I present this to accelerator physicists, they just scoff more or less, because everybody thinks to have an XFEL, you need to have a 10 GeV, and you need that very high energy. And we've labored to overcome that, but realized recently, and as we've learned a little bit more about electron microscopy, you guys are working at 100 or 200 keV, and you've got, density modulations in the electrons, which is exactly what we're after at the angstrom scale. So it's not, can you do it at 20 MeV? You can do it at 100 keV. There's a proof that you can do that. You can control those electron trajectories that well, and that's a critical thing for us. Because we're going to borrow your techniques to do that. So this looks just like the cartoon I showed before, except we added two things. We added something called an emittance exchange beam line in here, and I'll spend a couple of slides going through that. And we've added a nanocathode, and I'm gonna show you an updated method, but this was the original idea published a couple of years ago, was to make a patterned beam coming out of the cathode, and then re-image that downstream after acceleration. But what emittance exchange does, it's a very strange property, it exchanges from the transverse dimension, so from x and x prime, which is the angle of an electron with respect to the axis, into the time and energy domain. So it exchanges one phase space plane into another, longitudinal and transverse. It's as if you have a laser pulse, and you've got your laser waste and your divergence. If you could convert that into the spectrum and the pulse length of the laser, it'd be miraculous, right? You could do it with light, but it turns out we can do it with particles. And this has been proven. It's not speculative whether it works or not. It does work. The experiments have been done using entire electron beams to do it. So the innovation that I saw was to say, what if we had a nanometer structure on that electron beam in the transverse dimension, like you can make with a nanostructure or something like electron diffraction? Could we then convert that into the longitudinal dimension, and then we've got our spacing. If we can get our spacing just right, then we can emit coherently. So I'm going to describe the emittance exchange a little bit. It's complicated, and I'm not going to try too hard. I just want to show you at least how we can couple some of the different dimensions. If we take our electrons from the Linac and we just put them through an ordinary dipole, well then, the on-energy electrons will have some bend angle and go to the next dipole and come out straight. If you have an electron that's at a different energy, it will have a different bend angle, it won't bend quite as much. And so when it goes through this second dipole, these guys will be separated by some distance. And so what have we done there? We've taken two particles, they could have had any relationship spatially before, but they have different energies, and we've converted that into a difference in space. We've converted that into a spatial dimension. So that shows you how we can couple a dimension. And then this, so I'm showing the entire emittance exchange beam lineup. I should explain that. It consists of what we call a dog leg, which is these two dipoles, an RF deflector in the middle on the second dipole, second dog leg. The RF deflector is not it is accelerated cathode, it doesn't accelerate in the longitudinal dimension. Depending on when the particle arrives, it's deflected to the left or the right. You're setting a different mode of field. And depending on if the particle arrives early or late, it deflects left or right. And so that's showing you another coupling, where we're coupling the time of arrival into the angle. So I showed you, coupling energy to space and coupling time to angle. And you'll just have to trust me that when we put the strengths of these things together just right, you can completely decouple the previous motion and exchange these emittances entirely. It's really very interesting. I should have a reference up there. There's Paul Emma and Max Bernacchi invented this some years ago. So the job for us is to take a nanostructure on the beam in the transverse dimension and use that trick, that EDX line, to swap it into the longitudinal dimension, and then just put it into the inverse confidence category. You put it into an undulator too, and it would also laser coherently. Although I don't think you could keep that structure for the kilometer-long slap of the neck. I think being a meter long is a major advantage here. So work by Carl Bergen's group and Velasquez's groups. This is nanostructure. They're making these cathodes over the last couple of years. This was part of a DARPA grant. And at different scales. So depending on what fabrication process you're using, you can get down to nanometer scale, and with their electron deposition, they can get down to the kind of tens of nanometer scale. And so we can make point emitters, or we can make lines too. I like the lines. When we do this emittance exchange, we exchange one transverse dimension, not both, but one, say x, into the time z dimension. And you can just see, if we are emitting electrons off of each one of these stripes and nothing in between, you can imagine that's exactly what we're looking for. We just need to re-image that cathode way downstream. I should mention that the the pattern is completely washed out within 10 or 20 microns of emission. It disappears spatially, but it's still there in the momentum of the electrons. And we've done the simulation. We show that we can, at some level, reproduce it. So now this is kind of showing you what goes on. At the cathode, we have a bunch of emission points. If you look in phase space, the transverse phase space, each one of those little beamlets takes up some x and x prime that are separated. We use normal photo emission, or you can use many mechanisms. We're going to use photo emission, and there's no structure in the current at all during the emission, during the 100 femtoseconds or so of emission. And so there's no structure in the energy time domain. But we go through that emittance exchange device, and we take the phase space of this guy over to here, and the phase space of the transverse into the energy time dimension. And if you do things just right, you get these little current spikes that you can coherently emit at the period of the small bunches. So there are some funny things here. I'm not going to have time to go into all of them. But if we take this beam before emittance exchange and focus or defocus it, we're bringing that pattern closer or farther apart. We do the emittance exchange and we change the period downstream. So this is completely tunable. You're not fixed by your cathode spacing. And in fact, because we accelerate enormously from rest, where the electrons are at millivolt energies up to these MeV energies, we can demagnify tremendously this pattern. So we can demagnify from tens of nanometers down to nanometers. So that was the original idea. But just about a year ago, a young guy that works for me, Emilio Manning, proposed a new approach based on electron diffraction. And I think this is just a great idea. And it solves some problems that we would have. One is that producing the electrons at the cathode, you've got space charge forces. The electrons feel each other. It goes as 1 over gamma squared. So when they're at rest and before they're accelerated, the space charge forces are very strong, which is why we try to accelerate them very quickly. And so right when we have our maximum density modulation, we also have the maximum space charge forces, and that's tough to overcome. We need that cathode to emit electrons. We don't necessarily need it to pattern them, but it's got a job to do separate from the patterning, and coupling them complicates things. And we can only do what we can fabricate in terms of the cathode. It's kind of tens of nanometers and really very good. The electron diffraction, we can go, depending on the method you use, you can of course go down to the angstrom scale. You can do it at relativistic energies, not mildly relativistic energies. And you decouple the emission. So it really looks very promising to me. And we've got some recent simulation results on that. And this is actually, Emilio was looking through the textbook, trying to understand some of the optics we were doing, the electron beam optics, and came across this. This is a problem for the electron guys, right, for the microscopy guys. This is when you have a wedge of material that is not parallel faces, and the electrons are diffracting through that material. Depending on the thickness, they'll diffract either into the forward dimension or into the first order diffraction, and so you'll get alternating, dark and light depending on the density. And he saw that and said, well, geez, that's not a bug, it's a feature. It's exactly what we need. So we set up a model just downstream of the gun. Now we have our normal gun, we get rid of our nanocathode, have a conventional cathode, very low risk, and then we focus the beam at the diffraction sample. We can use just a standard silicon crystal to do this diffraction. And these are the dimensions of what we've been looking at. We're looking to make eventually 1 nanometer radiation, and for that we want a longer period of the crystal. And so just by setting these ratios correctly, we can have an alternating, either diffracted into the forward order or into the first order, and block one of those beams. And then just transport the unblocked beam normally and go through the emittance exchange. You have to do a certain amount of matching, and you can re-image that diffraction pattern downstream. And we've gotten that to work pretty well. This is showing now the simulation after acceleration and emittance exchange. And you can see, obviously, it's not beautiful upright bunches, but you can see near the axis we've got a significant density modulation. And if I just now Fourier transform the periodicity of that, I've got what we call the bunching factor, which is just the Fourier amplitude at that frequency of much higher than the background. And that's all I need in order to start this coherent process going. And we get a natural demagnification, so we knew we were aiming at this 1.24 nanometers, which is 1 kV photons. And so this looks pretty good. I then take that beam and run it through our standard FEL codes, Genesis FEL codes, what we designed LCLS with, and we can predict how many photons we get out. We need a very good beam in order to do this, so we work with extremely low charge so far. We'll see how, as R&D goes forward, how aggressive we get. But we start with a pico, just 1 picocoulomb off the cathode, and we get about half a picocoulomb we transmit it through the crystal. And these are some FEL gain length about 220 microns. That's 220 period per micron laser. That's right. We're going. I have to just be careful that we've done some simulations here. So we're at 400 periods at 10 picoseconds. Anyway, let's get to the punchline because we're in the end here. We get, this is the FEL output. We get about 10 to the 7th photons per shot. The nice thing is that they're fully coherent. We get about a 30 femtosecond long bunch with a single spike in the spectrum. And that's because we've got this pre-bunched electron beam. It's not starting up from noise, but we've arranged those electrons with that nanometer scale, and we've got them to go. So this is some number of photons. Because the phase space of this coherent pulse is extremely small, we have an extremely high brightness. This is an average brilliance similar to the APS ring. It's 10 to the 18th per second. They're about 10 to the 20th. And a peak brilliance of about 10 to the 28th. LCLS for comparison is about 10 to the 32. So we're up in that ballpark. And this is just putting everything on the same plot. This is our incoherent CXLS. Showing you how it compares to the big rings. And our average brilliance is here, similar to the 3rd generation machines, a little bit down. And the peak is well up above even the major machines, and not quite up to LCLS standards, of course. Okay, so that's about it. So I think we can make a low-risk hard experiment machine today. I think there's a nice method to convert it into an XFEL. And there are many applications for this machine that aren't accessible in big machines. Thank you.
Great, questions? Yeah.
I have a really simple sort of crass question. How much do one of these things cost?
$3 million.
$3 million.
Right.
I have a question to the sustainability. Therefore, the public utility cannot fit the bill for an LCLS energy cost alone. What will be the energy cost calculated for the coherent and incoherent compact source?
It's not high. The energy cost doesn't change at all between the two. All we're doing with the coherent source, we're just extracting more energy out of the electrons, but otherwise they're unchanged. It's under 100 kilowatts average power, wall plug power with everything. I don't know. I think
If all 500 kilowatts, especially compared to there was a.
Oh, this slack is, yeah, no. 10,000 times.
Therefore, your X-ray efficiency is very high. Therefore, the transfer from energy to
yeah, if you compare wall plug power and wall plug power to number of photons, that would be higher. I haven't done that, but that's interesting.
Yeah, in the non-coherent version, it's just, it appeared that your X-ray beam had quite a high angular divergence.
Yes.
And isn't that going to be a bit of a problem if we want to do X-ray diffraction from large period crystals or whatever, like proteins?
We can talk. We have developed collimating optics as well.
Then you cut down your flux, don't you?
No, we don't collimate with a hole. We collimate with optics. We don't throw out all those photons. So what has to be conserved is the product of the source size and the angular divergence. We have a very small source size and large divergence. We can convert that into a larger size, like a synchrotron, 100 microns, and a much smaller divergence.
And the X-ray optics is good enough to do that?
Yes.
Bill, the question about you using a wedge in the pendulum effect, you really want to be interested in that. If that's what you want, then the wedge will have a lot of inelastic electron scattering. What the community which does electronography has decided, because of that, is to use a bipolar, where there's no inelastic scattering. It might be an alternative world. Anyway.
Yeah, I might say it anymore. I want to come back to the comparison with the non-coherent source with the synchrotron.
Sure.
You said that you have similar flux than synchrotron, but focused on 5 by 5 microns. That means on the spot of something like a 5 or 10 micron crystal, you would have something like a factor of 500 to 1,000 times more photons.
Yeah.
That means it would be actually superior to a microfocus beam like the AES.
I doubt it. That's a short answer. The longer answer is, I think that the flux that those beamlines are using is what the maximum they found they can use while avoiding damage. At some point, you can't. It doesn't help to be more intense. And I think my understanding is they're around that point.
Because what we like to do when we get the compact source in the ASU is to essentially combine it with a jack, so that you would essentially do serial accelerators as has been shown at ESF. In the serial mode, that means you will not care about damage because you will direct to actually one way.
Yeah. So you can
Well,
I'm wondering the difference between theory and experiment. Because we're Sarah Dyed is a little hardware experiment guy. An electron microscope is trivial in theory, it's just a bunch of lenses, but getting it to work to spec is another matter. How far is this from delivery, from operation?
I don't think it's tough. I've commissioned several FELs, and there you fall off a cliff when you miss one of your parameters because it's an exponential process. And so, you have nothing until you have everything. It's this here, everything is linear. If our laser spot is too big or we have some timing jitter, it will affect the average, but it's just a linear scattering process. I don't think it's too bad. And the equipment we're buying is really, we're benefiting from the FEL development. It used to be that Linacs were just injectors into the big rings, and nothing they didn't make very stable power supplies, magnets, RF transmitters, and so forth. But FELs have driven this real push toward this high precision, and so we take advantage of that. I think it'll be okay.
I'm making very short laser pulses, X-rays, and I'm curious what the timings you expect to see for this limited low spectroscopy and synchronizes with other pulses and so on.
It'll be extremely stable. We've been very sensitive to that. Before I worked on this compact source, we were proposing these seeded FELs, so we used a laser seed. And the whole point, I work closely with David Mumpton, who you mentioned, and what users at Synchrotron have come to expect is this extraordinary stability that you can go there and the beam is utterly stable. So we've tried to incorporate that from the beginning.
So you expect to be under the 30 femtosecond also as well?
Yeah. The other part of that is it's easy to stay, Franz Herder is famous for doing this. He's under a femtosecond stabilizing lasers to RF in his lab. When you go do this over a kilometer, it doesn't work as well. I think they're at tens of femtoseconds. And for us to do this in one simple loop in the lab, I think we'll be down in the single femtosecond range.
Good.
Have you already started building the non-coherent source?
Yes, we started and stopped. We had a nice DARPA grant that got canceled in the sequester last year, so we began and we bought some of the long lead equipment for that.
So which parts already exist?
the Klystron and its power supplies.
So you told me that when we would give you the money now, you could have the thing ready, the non-coherent version in 18 months, which is really impressive. And then you can get it over here, and we have the ready. So how long will it actually take to show the proof of principle for the upgrade to the XFEL?
Well, if things went well, I mean, if that was the add-on for that, we had 4 dipole magnets and a kicker cavity. It's not exotic stuff, and the electron diffraction. So, if you have any good electron diffraction people around, it's an open question. You know, if things went well and we knew what we were doing, there's no reason it wouldn't just work. But it never goes like that on the first one. So I'm sure it would take hopefully a couple of years to build the equipment.